This video is going to cover allowable stress and the design of connections. Effectively, this is the same as just calculating stress, except this time you're going to be given stress and we're going to either find the load that it can carry or we're going to find the area, or probably in that case a thickness, a width, or like a diameter of a connector piece or a pin or something like that. So it's the exact same equations except it's in reverse. This time we're not finding stress, we're given stress. And usually we like to have factors of safety involved with things, and the factors of safety are involved because we don't trust that the construction is going to go in such a perfect manner that everything is built exactly down to the 0.0000 inches away from the exact spot it was supposed to be at in the design. Or that your loads are 100% exactly what you said they were, or that the material is a constant value all throughout. So because of this, we're going to have factors of safety, and our factors of safety, they're always greater than 1 because we're trying to be, safe. And factors of safety, there's 2 different types of factors of safety. One's for design, one's for analysis. So for design, we have a failure amount for our stress over an allowable amount that we want for our stress. So you say if it's going to fail at 50 KSI, maybe we don't want to allow it to get anywhere near 50. Maybe we want to say that we're going to put an allowable value of 35. And that's going to give us a certain factor of safety. Or usually we say, hey, we want a good buffer. If it was a factor of safety of 1, then your failure would be your allowable, right? So we want to always be greater than 1 with our factor of safety. So a lot of times the book that we're using does like to do something like 2.5. So we're, 2.5 times safe here, just to make sure that, things could change in the future for whatever reason. So this is our design 1. So if we are designing the size of a connection or something like that, or the size of a plate, if you're picking a size for something, that's design. And we also have our other version for analysis, and that one is the allowable over the actual. So this is our analysis 1. And again, maybe you want to know, hey, do we exceed the factor of safety? We want to make sure we're safe right now, but the client has decided to put more load on this. Is that still going to be okay? That's a pretty common occurrence, actually. So we have given numbers for load, for area, and we're going to then know what our actual stress is. And we have perhaps maybe an allowable limit that we want to not hit based on a factor of safety. So if you know the actual, then we're in an analysis, and if you know the failure, then you're in design. And allowable, you can see, is kind of like in between. It's in both of them because, again, we really, really, really don't want to ever hit that failure so we're going to design for a little bit less. So we're going to allow you to hit something a little bit less. And even then in the analysis part, even with that less allowable value, you still want to be far away from that. So it is kind of double compounding sometimes. Maybe it's not. Maybe your allowable even is your failure in terms of analysis. So there's 2 different ways to think about it. If you're trying to pick a size, we're in design. If you're just verifying whether or not it's okay, that's analysis. So what we're going to do now is hop over to a very wonderful example. This is going to be a design of a connection. So here in this example, we have a beam. It's not exactly fixed. It kind of really doesn't matter here, but we have a beam whose length is 12 feet, and he has a uniformly distributed load of 100 pounds per linear foot sitting on top. What's going on with those little orange blocks is that we are attaching this beam, say it's made out of wood, and we're going to attach 3 nails to it, to a plate, and then that plate is going to be then attached to the wall. So, and that's happening at both ends, A and B. We're going to have 3 nails each, and these nails have a failure shear stress of 30 KSI. We want to use a factor of safety of 2, and we want to know what's the diameter of the nails that we can use to the nearest eighth of an inch. All right, so step number 1 in doing this, we do actually need to know our load, right? So what is our load? If we're using our shear stress, that's going to be shear over area. And again, we want to actually find this area due because we want to know the diameter of the nails. So we don't have area, but we do have our stress. We're going to be able to find that, but we do need to find Mr. Shear. So we're going to draw us a free body diagram. Not really to scale here because it doesn't really matter. So it's 12 feet wide, and we have our uniform 100 pounds per linear foot. That's just pounds over feet. And I'm going to find what AY and BY are. Technically at this point, you may recognize that this is very symmetrical shape, and you might say that you can easily just divide it by 2 and say half the load goes to the left and half the load goes to the right. In a symmetrical case, that's pretty cool. That does in fact happen, but let's not do that. Let's actually solve for our stuff just to prove that it does work, and mostly just to make sure we're not being dumb. So we're going to sum the moments about A and set it equal to 0. So we're going to take counterclockwise positive, and what do we have? We have that 100 pounds per linear foot, but he's going to be going that direction about A, so that's going to be negative. So I have minus the 100 pounds per foot here across 12 feet, right? So across 12, again, that's in feet. And then we need to take the distance that the centroid of that distributed load is to the point of our moment, which is A. So that's going to be 12 divided by 2, and that is, of course, a distance in feet. So even if you don't like writing units, please write your units somewhere, either like on top of the equation, below the equation, whatever. So make sure that you're actually crossing out your units and discovering that we are still going to be in pounds and feet. Usually this is where people make a lot of mistakes. It's forgetting that, oh, you forgot to multiply by the distance that the centroid is from the point, or so on and so forth. So if you are paying attention to your units, it does make things a lot easier. And then we also have BY, but BY is going to be going positively around. So then we have plus BY, and BY's distance over to A is 12, and that's in feet. So BY, we're going to be getting his answer in pounds. And what did we discover? We discovered that BY is equal to 600 pounds. Now it is positive, which does mean that the arrow that I drew is correct. So it is up. And now if you sum the forces in the y direction and set it equal to 0, we have AY who goes up. We have the 100 pounds per foot that goes down, but that's in pounds per foot. We do need to multiply by the total feet that it's across, which is 12. So 12 feet, and you notice, yep, feet cancel, I'm left with pounds. And then BY also goes up, so that's plus 600, and again, that's in pounds. So therefore, we're going to get AY, and AY is also, wow, who would have guessed it, 600 pounds. Yep, and he's also going up. So did that whole symmetry thing work? Yes, it did. But when in doubt, don't just do symmetry. Please actually use the equations of equilibrium. So cool trick, but don't use it too often unless you really know what's going on. So now that we found it, we do actually have our shear force, right? Because technically at AY and BY, these are going to be our shear forces that act across the plane. So we're just going to imagine here, I'm just going to draw this pretty big. We have our block. I guess this is B because that's the side I drew it. So we have BY here. This is my 600 pound force. And what's really going on is I'm going to have a plate that's going to attach. It's going to be like an L plate perhaps. So it's going to attach to my block, and I said 3 nails. And then this piece is going to, with 3 other nails, 4 other nails, I don't know, attach to a wall. So we have our, you know, maybe we have another thing going through here. Right, there we go. So sorry for the really terrible drawing there, but that's kind of what's happening. So we've got nails that are going into the wood. That is our beam. And there's our force. And of course, there's our connections. So we're going to assume, and it's effectively for either one, that this is entirely fixed and not moving. So it is going to resist our force by going the opposite direction, right? Because it's not moving. So this is also going to be 600 pounds going the other way. So there we go. So we have our two things. We have, you can see our shear force is 600 pounds here, and it's going to be applied across these three nails. So if this plate with the nails is stationary and I'm trying to move the beam upward, the only thing that is resisting it are these three nails, and the diameters of those nails are the only things resisting it. So technically we're looking at 3 shear planes. And those 3 shear planes are, of course, the areas of the nails themselves. So the area that is, of course, the shaft of the nail, maybe you want to say it that way. So our equation for shear stress is going to be V, which we know that to be AY or BY, over the fact that there are 3 shear planes times area of the nail. Okay, so that's our equation. However, we don't actually have our shear stress yet. We have the failure stress and a factor of safety. This one needs to be the allowable. So before we can even start using that equation, we have to go back to our factor of safety. So our factor of safety, again, is going to be, because this is design, our failure over our allowable. So we said a factor of safety was 2.0 and a failure shear stress of 30 KSI. So we have 2.0 is equal to 30 KSI over our allowable stress. So very easily, our allowable stress is equal to 15 KSI. I used 2. Actually, in what I was looking at, it's supposed to be 2.5. So that's actually different here, right? If that's 2.5, then this is supposed to be 12. It would help if I could read my own handwriting sometimes. So anyway, we have a factor of safety, this time 2.5. 2.5, so a little bit more cushion, It doesn't really change much. 30 divided by 2.5 is 12. Cool, so this is our allowable value. And again, we literally just said that our allowable value is equal to our shear amount, which is 600 pounds, divided by 3 times, we'll put it in a new color, the area required. So here's the problem. You're looking at your units. If you're actually paying attention to them, you cannot just start multiplying and dividing and go in every which direction, because one of them is in kips per square inch and one of them is in pounds. So before we get too far, let's change our units. We have 1 kip is to 1,000 pounds. So what that's going to do for me is that's going to cancel these pounds. Now it's in kips. Both sides are in kips. So I'm going to get my area then in square inches. So my area that I'm going to find, this area required, is going to be 0.0167 inches squared per bolt. Right, per bolt, because there were 3 bolts, or bolts, nails, but per nail, because there are 3 nails, this is the area per nail. So now we know our area equation for a circular thing is pi divided by 4 times d squared. So we're going to be able to get a value for d. Put it in another fun color. This gives us D required is equal to 0.1457 inches. And we said we wanted it to the nearest eighth of an inch. This does not mean, this nearest eighth of an inch does not mean round to the nearest eighth of an inch, because the question is, do you round up or do you round down? And that is dependent, of course, on this entire string of things. We started with the factor of safety, we got a T allowable, from there we got an area required, from there we got the D required. So let's check it out. Let's do a little trial and error and see what happens. The nearest eighth of an inch, and an eighth of an inch is 0.125 inches. The second eighth of an inch that we have is 0.25 inches, which is actually a fourth. So which one do we do? If you're thinking nearest, you're probably thinking, okay, so I'm going to round to the one that's actually closer. You're probably thinking it's this one. Let's try it out. Let's try it out. So if D is equal to 0.125 inches, that's going to give us an area of 0.0123 inches squared. And that's going to give us an allowable stress, plugging that back in to here. You just have 600 divided by 3 and divided by that area, which is 0.0123 inches squared. So we're going to get an allowable stress value of 16,260. And of course, that was pounds, 600 pounds divided by 3 divided by that. So that's PSI, which is technically 16.26 KSI. And I think we don't really have to go any further than this. If you got, it's not really allowable at this time. At this point, it would have been actual. If you got an actual value of 16 KSI and you were only allowed to have 12, obviously you can see that this was a no good. You can go a step further, right? If you take this, if you kept calling this allowable, if you called that allow, and you took this a step further and you said, well, we had the 30 was our failure, and we put that over our 16.26 KSI, we're going to get a number that, as you can tell, this is 16 is greater than 15, so this number is going to be less than 2 for our factor of safety. And our factor of safety was supposed to be 2.5. So hell no, that's definitely not good. A larger factor of safety is always good. You don't want anything less than what you had before. So bigger factor of safety is always better, which does mean that now that we got all the way through this, we realized that the number that we had chosen, the 1.25, is not good. So the actual answer to the nearest eighth of an inch, the D that we're going to use, the D required that we're going to use is 0.25 inches. If they want it to the nearest eighth of an inch, that's our answer. We cannot go less than that if we're going in terms of eighths of an inch. If we do, then obviously it's not going to be good with our factor of safety. So allowable stress is not terrible, right? Same equations back and forth. The only thing that's different is, of course, check your answer. Always, always, always check your answer. Go back through and see if you have violated with your new design choice your allowable stress. That's it. So we're just going in reverse, but you'd always, always, always check your answers and make sure that they work out.